All right, today we're going on a bit of an adventure. We're going to map the entire universe of numbers. And I mean everything, from the simple numbers used to count your change, all the way to those strange, mysterious numbers that seem to stretch on forever.
So, let's kick things off with a huge question. What if you could take every single number you can think of, 1, a million, -5, even something wild like pi, and give each one its own unique spot on one single infinite line? You see, this isn't just some boring tool from math class. It's a map to a hidden universe, and we are going to explore it together.
And this map, well, we call it the real number line. It's just a perfectly straight line stretching on forever in both directions. Now, the most important thing to get your head around is this. Every single point on this line, and I mean every point, corresponds to a unique number. Every number we talk about today has its own home address right here.
And that brings us to the official name for these numbers, real numbers. You'll often see them written with that cool-looking R with the double line. But what does it mean? Simply put, a real number is any number you can find on that line. It's the whole shebang, the complete set. It includes both rational and irrational numbers, which means the line is perfectly continuous. There are absolutely no gaps.
Okay, and this right here is a huge tip, especially if you've got an exam coming up. The real number line is continuous. What that means is, if you were to zoom in on any tiny little piece of this line, I mean a microscopic piece between two numbers that are super close together, you'd still find infinitely more numbers packed in there. It's completely, densely, mind-blowingly full. So who exactly lives on this infinite line? Well, a great way to think about the number system is to picture a set of those Russian nesting dolls. You know, where you open one up and there's another one inside, and another inside that. We start with the smallest, most basic family of numbers, and just keep adding new types to create bigger and more inclusive families.
We start with the smallest doll, the natural numbers. These are just your basic counting numbers, 1, 2, 3, and so on. Then we ask, hey, what about 0? Boom! Add 0 to the mix, and you get the whole numbers. Then we add all their negative opposites, and now we've got the integers. And the biggest doll, for now, is the set of rational numbers. This group is huge and includes any number that you can possibly write as a fraction, which covers all the integers plus every decimal that either stops or repeats in a nice, neat pattern.
Okay, now for something really, really cool. What if I told you that basically every number has a secret code? I mean, a unique identity, like a fingerprint or a strand of DNA that no other number in the universe shares. This isn't science fiction. It's a universal law called the fundamental theorem of arithmetic.
So what does this powerful theorem actually say? Well, it states that any composite number, and that's just a fancy word for any number that isn't prime, can be broken down into a product of prime numbers. But here's the magic part. That specific combination of primes is completely 100% unique. The number 36, for example, will always be made of 2 2s and 2 3s. Always. It can't be anything else. That's its fingerprint.
So how do we find this unique code? Well, we use something called prime factorization. You've got a couple of methods. On the left, you see the factor tree. It's really visual and great for smaller numbers. On the right, you have the division method, which is a bit more systematic and, honestly, better for bigger numbers. But either way, the goal is the same. You just keep breaking the number down until you're left with nothing but primes. For 36, that unique code is 2 times 2 times 3 times 3, or, as we'd write it, 2 squared times 3 squared. So, why is this number DNA so useful? Well, it is the absolute perfect tool for finding the highest common factor, or HCF, and the least common multiple, or LCM. For the HCF, you just look at the prime factors that the numbers share and take the smallest power. For the LCM, you do the opposite. You take the greatest power of every prime factor involved. Oh, and you've got to remember this crucial formula. For any two numbers, if you multiply their HCF and their LCM, you will always get the same answer as multiplying the two numbers themselves. Super handy.
But what if the numbers are huge? I mean, what if prime factorization would take you all day? Well, luckily for us, over 2,000 years ago, a brilliant mathematician named Euclid came up with this incredibly elegant and super efficient shortcut for finding the HCF.
Now, his method is based on an idea that sounds complicated, but is actually really simple. Think about it. If you have a bunch of items, say A items, and you want to put them into groups of B, you'll end up with a certain number of full groups, that's your quotient, Q, and you might have some leftovers, that's your remainder, R. And that's it. That's Euclid's division lemma. It's just a formal way of writing down that simple process of division.
So using that simple idea, we get this algorithm. I like to call it the stair-step method. You just apply the division lemma once. Then you look at your remainder. If it's 0, you're done. The divisor is your HCF. But if it's not 0, you just take the divisor and the remainder from that first step and you do it again. You keep taking these steps down until that remainder finally hits 0.
Let's see it in action with 225 and 135. First step, 225 divided by 135 is 1, with a remainder of 90. Okay, not 0. So now we take our old divisor, 135, and our remainder, 90. 135 divided by 90 is 1, with a remainder of 45. Still not 0. So we do it again with 90 and 45. This time, 90 divided by 45 is 2, with a remainder of 0. We stop. That last divisor we used, 45, that's our HCF. See? So simple and so elegant.
All right, we've spent a lot of time with the rational numbers. But what about those other, more mysterious residents of the number line, the irrationals, like the square root of 2? How can we be so sure it can't be written as a nice, simple fraction? Well, we solve this mystery with a clever logical trick. It's kind of like being a detective. The tool we're going to use is one of the most powerful in all of mathematics. It's called proof by contradiction. The basic idea sounds a little backwards at first. To prove something is true, you start by assuming that it's actually false. Then, you follow that assumption down its logical path until you run headfirst into a wall, a contradiction, something that makes no sense. If you find one, it means your starting assumption had to be wrong all along. So let's be detectives and investigate the square root of 2. Step 1, the assumption. Let's pretend the square root of 2 times rational. That means we can write it as a fraction, a over b, in its simplest possible form, right? No common factors. Okay, step 2, the clue. If we square both sides and move things around, we get 2b squared equals a squared. This tells us that a squared must be an even number. Step 3, the deduction. Now here's a mathematical rule. If a number's square is even, the number itself has to be even. So a must be even. Now for the twist. If a is even, then a squared must be divisible by 4. That means 2b squared is also divisible by 4, which in turn means that b squared has to be even. And if b squared is even, then b must be even too. And wait a second, hold on. We just proved that both a and b are even. But our very first assumption was that the fraction a over b was in its simplest form. If both numbers are even, it can be simplified. That's our contradiction. It makes no sense. The only possible conclusion is that our initial assumption was dead wrong. Case closed. The square root of 2 has to be irrational.
Okay, so if dealing with fractions and proofs can be a bit tricky, what's the final telltale clue to a number's real identity? Well, it's actually hiding in plain sight. It's the number's decimal form. The way a number behaves after that decimal point tells you everything you need to know.
And here's another awesome exam trick for you. How can you tell if a fraction is going to create a decimal that just stops or terminates without actually having to do all the long division? The secret is all in the denominator. Look at its prime factors. If the only prime factors you find down there are 2s and 5s, that decimal will stop, guaranteed. If you find any other prime factor in there, like a 3 or a 7 or an 11, that decimal is going to go on forever in a repeating pattern.
This table right here really puts it all together nicely. It's the decoder ring for all numbers. If a decimal stops, it's rational. If it goes on forever, but it's in a nice, predictable, repeating pattern, it's also rational. But if it goes on forever with no pattern at all, just a chaotic, endless string of digits, like pi or the square root of 2, then you, my friend, have found an irrational number. It's really the final piece of the puzzle. So there you have it. We've journeyed across the entire real number line. We've met all its different families, from the simplest counting numbers all the way to those wild, infinitely complex irrationals. We've seen that the line is completely packed, with no gaps whatsoever. But that leaves us with one final fascinating thought. If this line contains every single real number, could there be numbers that exist off the line?